deeper concepts. Work, power, and energy. And, you know, you're right, because we're going to do work, power, and energy. Well, that's because we have a whole lot of other stuff to do in engineering. So we don't really spend a whole lot of time to talk about like the mathematical foundations of why this stuff does what it does. That's more for like the physics standpoint, and here we are in physics class, so that's what we're gonna do. So we're gonna specifically start going over like why work is what work is and how it relates to energy and how it relates to power. Why they call it work power energy is we normally do power at the end because power is related to energy and energy is related to work. So like there's a hierarchy here. You probably should have experienced some of this stuff in ninth grade. So like whenever I say a couple of things, it shouldn't be like completely 100% new to us. Like the concept of work. If I'm talking about work, what does that mean? If I were to say I'm going to do work, expend energy, I would go with that. That's a pretty good one. So if you're going to do work, the definition of work is expending energy. Now, what do we normally expend energy to do? Literally everything. Okay, so well, okay, what is an example of doing work? Breathing. Okay. Lifting furniture, moving stuff, absolutely. So in other words, I think what y'all are saying to me is that in order to spend energy, you're causing motion to occur, right? I think in every situation that you can try to describe to me for work, there's going to be some kind of motion involved with it. So if there's no motion, there's no work. And this is where things get a little bit interesting, okay? Because this is what the concept of work is and the definition in and of itself of work. So the mathematical definition of work is going to be if you have a force and you multiply it by a certain distance that you travel. Now, one other thing that we need to add to this one is that the force and the distance need to be parallel to each other. So I'm going to make a little parallel symbol right there because if the force and the distance aren't in the same line with each other, no work is going to get done on that object because it's not going to move. Okay, so or so I don't know. Let's just go ahead and I'm going to go ahead and write this up here. Or force times distance times the cosine of the angle in between the actual useful force and the displacement. So your displacement and your force need to be parallel to each other. Like a good example is if you're pushing a box across a floor, then you're actually going to do work on it because you're going to push the box this direction, and the displacement that actually travels is going to be in the same direction as the force that gets applied. So in this case, this is a good indicator of how to use force times distance because the amount of work that you're going to be doing is just simply multiplying the two numbers together. So easily enough, if it's say got a distance of 20 meters and you've got a force of 5 newtons, then the work done is going to be 5 times 20. So the work done is going to be equal to 5 newtons times 20 meters, which equals 100 newton meters. Capital N, little m. Yeah, capital N, little m. So this is the metric system of pound foot. So there is a difference between a foot pound and a pound foot. Pound foot is work. Foot pounds is torque. Yeah. And we're actually gonna that's the difference here too. Okay, so we use a different version of torque than we do Newton meters. So for us, Newton meters is the definition of work. The English equivalency of this is going to be a foot pound, not a pound foot. Okay, so it's a little weird, it's a little different, but fortunately for us in AP Physics, we don't touch the customary system with a 10-foot pole. Everything is going to be KMS, and we're fine. The Newton meters is can be simplified. So I'm going to highlight this. Newton meters is a specific type of unit, and that specific type of unit is called a joule, capital J. Okay, the joule is the unit of energy. The joule is the unit of energy. Now, it's spelled after an old dead guy, Joule, joule. Okay, so if I say that 100 joules of energy was spent, then we know that we're expending some kind of force times distance, or we're expending some kind of energy. Now, this is just the tip of the iceberg. There are tons of different ways that we can express work being done. Force times distance is the most common and most basic way to do that. So we're going to be continuing to expand our bag of tricks as we continue going. Now, let's look at the wrong way to apply a force times distance. So if the distance is right here, going this direction, and you've got a box here, you can't stand on top of the box and push it downwards, okay, and expect it to move. Because, I mean, you can ask yourself this question: am I exerting a force on the box? Yeah, absolutely. But there's no displacement that's occurring because my force and my displacement between the two, like the direction of motion, the force is not going in the direction of motion at all. And since the force and the direction of motion are in opposition to each other, 90 degrees to each other, then there's going to be no motion occurring whatsoever. So in this case, even though you did exert a force on the box, there is no work being done. So no work. What I like to say is I like to say zero work. Okay, because for some reason there's a difference in people's brains between no and zero. So like I say zero because there is a force being applied. It's just that force really isn't working. So I try to use the term zero work instead of no work. I'm not perfect. Sometimes I'll say no work anyway. But I try to use zero because that kind of implies that we're trying, we're just being dumb about it. Okay, so like if you push straight down and you're wanting it to go left and right, that is not going to work out for us. Okay, everybody alive so far? Wheels are useful because wheels lower friction, but you can still apply work using that same concept. Absolutely. All right, so next in line, let's see if I can get my go down. There we go. Um, if you're taking an object and you're pushing it along a certain direction, then the force that we're using only works in the applicable direction. So let's say that if you're taking an object and you're pulling it with a rope and you're pulling it upwards like this. So the rope isn't completely horizontal, but the direction of motion is horizontal. Like if you're pulling a box with a rope, you're not going to magically start floating in the air because of that. Be like, well, I'm pushing with an upward force, so I should technically float. Be like, that's not really what's happening. The direction of motion is going to be left and right. So that means if we take our force that we use, which would be this tension of the rope itself, we can break that up. So we can break that up into horizontal components and vertical components. And then I'm going to go ahead and put the letter theta, or yeah, the Greek letter theta in there. And we're going to have a angle. So in this case, this is where your horizontal force is the only one that's actually going to work out in this case. So the only force that I'm looking for here is this bottom force. I'm not looking for the vertical force. It doesn't matter to me at the current moment. Okay, I'm not looking for the tension, it doesn't really matter to me at the current moment. Um, we will need to at least know a number in order to be able to solve for this. And usually the easiest number to get on a measurement is to get the tension in the rope itself. It's not very easy to get the components of the force. You can also get the displacement as well too. Okay. So this is why I say that, well, this bottom force is going to be F cosine theta, and the top one is going to be F sine theta. And I'm writing through the person. That's okay. So we got F cosine theta. Yeah, it's their their wrestling belt. F sine theta. They know what's going on. They've got it. They've got the vertical force going. So in this case, it's force times distance. So the force is going to be F cosine theta, and the distance is just going to be whatever this distance is times d. We normally rewrite this, so we normally rewrite it as FD cosine theta. It's the same thing. Okay. But that's where the cosine of theta comes from. So if you're applying a force at an angle, you have to use the cosine of theta. Okay? Um, and the reason why we use the cosine of theta is because it's going along the direction of the motion. There may be really weird circumstances where you might actually have to use the sine instead of the cosine. So my best advice to us, like right now, is to always watch the direction of motion. Okay? So sometimes sine will be the one that it takes. So I'm going to say watch the direction of motion. And I'm going to try to come up with a couple of examples to where it would not be cosine, it would be sine instead. But we'll do those whenever we get to them. We're going to make ourselves go a little bit deeper in this work concept first. Okay, so you have to get energy from somewhere. Okay, and one of the best places where we can get energy from in terms of physics is we can get energy from gravity. So gravity's kind of weird whenever it comes to work. Say work and gravity. So we can do work against gravity, and we can also do work with gravity. So depending on what we're doing will depend on the actual circumstance. So let's I'm gonna draw a picture for an example. So you've got an object and it's on the ground. Okay? And you take this object and you pick the object up. So you're gonna move it from this location to this location. I'm gonna write I for initial and F to final. Okay? So my first question to you is, did we do work? We did? Okay. So the answer that y'all give me is yes. And why is that? Okay. And there is a distance that has been traveled. Okay. So the distance traveled would be this direction, right? So this would be my displacement vector. Now, what would the direction of my force be? Okay. Ooh, okay, so is the arrow pointing? So we're talking about the box, right? So is there a constant force being applied on the box as it goes up? What direction is that pointing? Why are you just staring at my pen and not answering by what my pen says? Gravity points down, right? Gravity always points down, right? So if you're pulling up and you are actually lifting an object in the air, then you are doing work against gravity. Okay? You are doing work against gravity. So the force of the arrow is always down for lifting a weight. So when you're lifting a weight, the arrow is up and the force is down. Right. They're actually it's actually like it's actually talking about the weight. So if you're doing work on an object, you have to do work on that object to counterbalance that force. Okay. So what are you doing? Like we have to really think like positives and negatives are going to make a really really big difference here, okay? So, since the direction and the force are opposite directions of each other, this is going to be a negative value, okay? And it's a negative value because we're working against gravity. Okay, we're doing work against gravity. So the direction of the displacement and the direction of the force are opposite from each other. And if we were to mess with those angles, the difference between the this arrow and this arrow would be what? If I were to put them right by each other like this, D and F. We really shouldn't mix vectors like this, but if I were to do that, what would the angle between those two be? Okay. And the cosine of 180 degrees is what? That is a really good question. I might have. Hey, I don't have a -1. Okay. It should. It says yeah. It should say -1. Yeah. If you type in the cosine of 180 degrees, you should get -1. So if we type this in and we do force, yeah, right. It never hurts to double check. So if we do force times distance, uh, y'all may be right. The pin may have decided to die out on me. So force times there it magically goes. Okay. I don't I don't understand why it's not working. Yeah, it's like magically working half the time, and then it's not working the other half the time. That's really weird. Magically decides to work randomly. I don't know. I don't have a good answer. Should let me write all of them, but it's not. It's doing its thing again to where it doesn't really let me erase. It's the potato. The potato is doing its thing, so I may have to turn it off and turn it back on again to get it to work. So yeah, the poor online kids. They're just like, what's happening? I don't understand. What's going on? Just close it back down and open it back up. I'm gonna open it back up and there's gonna be like 15,000 things up there. It is, yeah. It goes. We're thinking about it. Okay, we're gonna try again. Can I erase this? There we go. All right, the force and the displacement are opposite of each other. So if I were to have a force of, I don't know, let's just say that this is a 20 Newton force. Yeah, we work okay now. The 20 Newton force and the displacement is equal to, we can't really go too high. How about like 1 meter? Then that's going to be, 20 newtons. And then there it goes again. 20 newtons times 1 meter times the cosine of 180 degrees, and that gives you -20 joules. Okay, this -20 implies that we're doing work against gravity. Okay, so this is doing work against gravity. Ooh, is it? Uh-oh. Yeah, yeah. Welcome to, yeah, you're right. You're right. So it's -20 newtons, and that would, oh dear. And that would come out to -20 times cosine, and that would give you a positive 20 joules. So you'd have positive 20 joules equals this. There's a whole like spot down here where it doesn't want to work. So it's positive 20 joules. Okay. So my statement still remains. Maybe my computer was just like, stop with that negative business, Mr. Broadway. Stop it. That positive 20 joules means that we're doing work against gravity. So we're ending up storing an energy. That also means that if we go down, it should go the opposite direction. It should move downwards and it should have a negative value instead of a positive value. We can try that and see if it actually works and does its thing. Um, Apparently I can only get my top half to actually work. So yeah, and that's a good question because you've got positive joules and you've got negative joules, but there's not really it's probably important to go ahead and say right here, there is no such thing as negative energy. Okay, there is no such thing as negative energy. And that's probably a really important thing to say to you guys right now. Um, for right now, you should treat energy like money. Okay? Treat energy like money. Because, like, for example, if I say this, negative $20, okay, there's no such thing as a negative $20 bill. Nobody's going to hand you a red bill that says 20 on it. It means like, ha, this means you don't have 20. Yeah, right, exactly. There's no such thing as a negative $20 bill. What negative 20 means is negative 20 means you either spent it or you owe it, right? So in terms of energy, whenever we see minus 20 and positive 20 joules, this doesn't mean that we are this doesn't mean that we have negative energy. This means that we either spent that energy or we have saved it or stored it or loaned it in one direction or another direction. Okay, so whenever we're dealing with these concepts, we need to treat energy like money. Okay, because work is just the process of transferring that energy from one location to another location or from one process to another process. So work is how we actually achieve the transaction, and energy is like the money when it comes down to it. The amount of energy that you have in a system is fixed. You can take that energy and you can spend it in one spot and lose it in another, but you can't like have zero. Like, you can't have energy just like randomly appearing and randomly vanishing. The amount of energy that you have is the amount of energy that you have. Okay. Yeah, we can't reject money at this point because we kind of like money. I'm gonna try to restart it again and see what happens. Count to 10 real quick. Breathe deeply. My poor potato. Uh, Everybody else gets a nice fancy laptop. I get the potato. It's okay though. Yeah, I'm gonna try to close some programs so it doesn't like explode. Maybe it'll make our life a little bit easier. There we go. Okay. Don't touch. No, it's I think it's still doing it. Uh, okay. I have no idea. We're just going with half screen. I don't know. It scares me. If that fixes it, I don't even know. Right? It looks like it's like a completely different page that's open, but it's like a scroll bar magically appeared and just like I don't know. We're in halfsies mode today, guys. I don't know what else to say other than we're in halfsies mode. Hopefully this records even for the virtual kids. If it doesn't, I'll be doing it all over again or just linking a video online somewhere from somebody else. Okay. Um we're going to keep going. We're going to keep doing this. All right. So, if you take an object and you drop it off a cliff, then is work being done? Just take an object and just toss it and it goes down this way. The distance that gets traveled is the height of the object. So we're going to call that h for height, right? And it's got a mass, right? Why don't we just call it m, mass m? Well, what would be the force of that mass? Okay, force equals ma. Specifically, since we know that we're on Earth, it's mg. Okay, so there's a force that's going down. So that force that's going down is mg. Okay, and is the direction of motion is down this direction, right? The force is down that direction. So two negatives will end up making a positive. So we'll end up with work being spent. okay? Because you've got a negative force and you've got a negative height. The cosine of in between both of those angles is 0 degrees, and the cosine of 0 is 1. So even if you did the FD cosine theta, you would come out with still a positive value, okay? So here we go. The work being done going down this direction is going to be equal to mg h. Okay, the mg is the force and the h is the distance. That's our force times distance. And in this case, if you're just dropping something off of the ground, the cosine of theta, this is 0. Sorry, this is the cosine of theta. Theta is 0, so the cosine of 0 is 1 in this case. So your FD cosine theta can be really made a lot easier by just saying that it's mass times acceleration due to gravity times height, okay? And if you do that, it will tell you how many joules of energy that you spent going from one location or another. Another way to say that is it will tell you how much work you did, or how much, I'm sorry, how much you didn't actually do that work. If you take something and you drop it, you did not do that work. Gravity did that work, okay? Like, yeah, that is the exact same formula for potential energy. Yeah. So the amount of energy that we can store into something is going to be the amount of work that we can put into store into something. So work and energy is really just two different ways of talking about the same concept. Energy is the amount of storage that you would have, or the amount of capability to do work, and work is the actual process of spending it. Okay? So like for example, if you say I went to the bank and I saved up and I put $200 in the account, then you're telling me what you did. You're telling me that the work that you did, right? You could also say that your total savings is $200, right? If you just say my total savings is $200, you're talking about energy. If you say I stored $200 in the bank, that's talking about work. Okay, does that make sense? So work is your ability to actually spend the objects or store the objects, and energy is just talking about an amount. It's talking about like a quantity, how much energy that you have. Okay, and we can't get rid of it. We can only move it from one form of energy to another form of energy. Okay, chemical energy is totally a thing. Fortunately, we don't touch it with a 10-foot pole. The two big types of energy that we deal with here is we deal with kinetic and gravitational potential. Okay, so we deal with kinetic, we deal with gravitational potential energy, which I'll just call GPE, gravitational potential energy, and we'll also use spring potential energy. So that's SPE, spring potential energy. Okay, we deal with all three of these. Um, the kinetic energy normally gets the letter capital K, which everybody is just fine with and nobody has any hernias over. The second one, we're going to have some aneurysms. Okay, because G, gravitational potential energy, I'm pretty sure I've already told you all this, gets the letter U with a little G afterwards. UG. Okay, spring potential energy gets U with a little S. Okay. Now, last year, we took all three of these types of energy and we applied them together to make a little bugbear name, and we called it Kugus. Kugus, Kugus. Okay. In AP physics, kinetic, potential, and spring potential are really the only kind that we deal with. Okay. Is there a chemical potential energy? Yes. Are we going to deal with it? No. Is there a nuclear potential energy? Yes. Are we going to deal with it? No. Is there a, I don't know, electrical potential energy? We will actually deal with that, but not anytime soon. Don't worry about that one just quite yet. So in all these conservation of energy problems, whenever we're dealing with like energy being spent or work being used, we're going to deal with Kugus because we're going to have kinetic energy, we're going to have potential energy by a gravitational force, and we're going to have the potential energy by a spring force. Okay, so I guess since y'all already kind of jumped in there, potential energy is just stored energy. So if you can take energy and you can store it up, that's potential energy. Okay? And there are tons of different types of potential energies. Equals stored energy. Okay? And go up there. Um, Now, I think that I probably want to spend a little bit more time on the actual like work being done because there are a couple of weird caveats that we're going to have to apply that will make some like small differences to us. Um, One of them is if you take your force and you apply it at an angle, like on the box pushing one, there's a couple of things that happens to friction, and it depends on the normal force. I'm gonna go ahead. Is everybody okay with this right here? Can I move it? I'm on half C screen, so I need to probably wait a little while. I would start drawing my little ramp down here, but maybe I can. All right. So here's a here's a box and a ramp. There you go. Nothing happens. Like I mean, I don't know. I don't even know what this is to be honest. So there's a force acting on the rope, and we've got our horizontal and our vertical component. Now, if you're pushing up this way, and this box is dragging along a surface, a rough surface, the question I want to ask you guys is, um, does this increase or decrease friction? Why? You can't say pulls away from the friction. That doesn't make any sense. Okay. You're getting there. You're getting there. You're on the right track. So if I were to draw a free body diagram of this box, what forces do I have acting on it? This force going this way is there. Okay. Gravity, normal, and y'all just said all three of them. Yeah. So we've got gravity, mg. We've got the normal force in, right? And we got friction going backwards. Okay. Now, the force of friction is dependent on something. The force of friction is what's the formula for friction? There you go. Friction is fun. Yeah. So mu times n, right? Which means that our friction is always going to be dependent on our normal force. So in our normal force, we don't actually have to pull because we know that mg and the all of the forces going down and all of the forces going up have to be balanced to each other, right? Well, in this case, mg is going down if we use our sum of our forces in the y direction. We know that mg is going down, but there's not just one force going up. There are two forces going up. So that force of the y direction is going to be mg. I guess we're going to say negative is down, right? Is that okay? Negative mg, is that fine? Plus the normal force, plus whatever this is. Isn't that f sine theta, not cosine? It is not the same thing. Sine and cosine are not the same thing. They are not the same thing. Not even close. They are literally like the opposite ratio of each other. So sine, remember sine is going up and down normally if you're on a flat surface. Cosine is going left and right normally on a flat surface. So that means that our normal force has to be less because I know that this thing isn't really moving up and down. It's not floating in the air and it's not Hulk smashing through the ground. So this sum of the forces in the y direction has to be zero, which means that mg has to be equal to n plus f sine theta. That also means that the normal force has to, oh, there goes that screen again, right over here. That also means that the normal force is going to be equal to mg minus f sine theta. Okay, so your normal force is actually going to be smaller, and since your normal force is smaller, the coefficient of friction is not going to change. The coefficient of friction always just depends on the nature of the surfaces. It doesn't depend on the actual intensity of the force pushing down on it. Since the normal force goes down, then the normal force, oh sorry, since the normal force goes down, frictional force has to go down as well too. Okay? You had the yeah, you had you were correct, but your reasoning was I don't even want to say incorrect. I just want to say rocky. Like you didn't necessarily tell me exactly what I wanted to hear. Right. It wasn't wrong. It's just kind of it's just kind of haphazard. I think haphazard's probably a good way to call your logic there. Haphazard. Now, we can do the opposite scenario, and we can prove that the opposite scenario is true as well. We can prove that if you are going to push downward on a box and scoot it across the surface, that the friction will actually increase and not decrease. Yeah, and you can feel this. Like if you ever take a box and you drag it, like if you pull it this way, it's easier to pull because you're pulling up and the friction doesn't pull back as hard. If you take a box and you push down and you push it across the floor, it's actually harder to push. You can feel that if you ever get like some giant boxes to push everywhere. Uh, yes, yes, yes. They don't know, like, yeah, and that's a good point. Is like if you don't know how to do it, applied physics does come a long way. I mean, like, it's just right. Yeah. Yeah, so like if you this is automatically going to be harder. So if you take an object and you push down on it so that the force is going down this direction, that's going to be a downward component and a horizontal component that goes this direction. So there's technically has to be more normal force because there's a gravitational force mg and then there's a normal force n. Friction will be pulling back this way. Yeah, see how these two go in line with each other? So that means that in order for this to be balanced, in order to do Newton's second law, I always write I always write it as wait, let's see. I always write it as the sum of the forces in the y direction, and then I just write everything out. This is negative mg minus n, sorry, minus what is that? F sine theta. That is using here's the yeah, because here's theta. Here's the angle that we're using. So we're going to say F sine theta uh, plus n, and we know that's equal to 0. So that means that if I can actually write this in space, that means that n is going to be equal to F sine theta plus mg, which means that our normal force is going to be greater. And if our normal force is greater, then the force of friction has to increase as well too. So when you're dealing with this equation, you should always consider that mu to be like a constant value. So if your normal force increases, this frictional force is going to increase because of it in order for this equation to stay equal to each other, in order for the balance to be given. Mu does not change unless you change the nature of the surfaces. So if you're going from right. Yeah, if you do not if it specifically does not mention a change in surface, then the coefficient of friction is assumed to stay the same always.